Hi, I'm Rachel and I'll be talking about non-fossil fuel power production today. Although non-fossil fuels range from nuclear power to wave power, I will only be concentrating on hydroelectric and wind power because I have to stay within the time limit given by Mr. Abbott. So there are 3 questions about renewable resources that I'll be answering. What are renewable resources? Popular locations with renewable resources around the world, and which renewable resource is generated the most. Renewable resources are natural resources with an endless supply. It replenishes quickly and it is sustainable, which means our future generations can enjoy the benefits of these resources as well. Here we have a few popular locations around the world that generates green electricity. There's the Columbia River in US, which generates hydroelectric power, a wind farm in northwest of Iran, and just a little bonus, a solar power plant in Nevada, US. Now let's take a look at some statistics I took from Siemens.com. Take a look at the magnified pie chart on your right under renewable energies. As you can see, hydropower and wind power are 2 renewable energies that generates the most energy in the world. So, are you already curious about how electricity is generated with just wind and water? Let's talk about hydroelectric power first. Before we go into the technicalities on how hydropower is generated, let's take a look at the different hydroelectric schemes in the world. We have the pump storage schemes, which pumps water up into a reservoir and drives the turbines during the daytime. There is also the run-of-the-river power stations that generates electricity from water directed from fast-flowing rivers. This is an advantage because no damming is required to get the water to a certain height to drive the turbines. There is also the small-scale power stations that generates hydroelectricity for nearby housing or factory areas that requires large amount of electricity, and finally, tidal power, which drives turbines using the difference between its high tide and its low tide. Now let's take a look at my hydroelectric nodes. We can see that there's a mass of water at a certain height and it's going to flow into a narrow pipe to drive the turbine at the bottom. So at point 1 in the diagram, the mass has potential energy. PE, as we know, is equal to mgh, where m is the mass of the water, g is the gravitational acceleration of the earth, and h is the height the mass of the water is from the ground. Since we are talking about power, we need to incorporate a power equation in this situation. We know that power equals to energy over time. So in this case, power generated equals to potential energy over time, or mgh over t. Recalling that density equals to mass over volume, the mass of water can be rewritten as density times volume, where the density of water is always 1000 kilograms per meter cubed to make calculations easier. With that, we now have a cooler equation for power generated, which is PVGH over time, where PV now replaces the M from line 2. Before this, I mentioned that the water flows through a pipe to turn the turbines. So we give the volume flow rate through the pipe, which is V over T, a quantity Q. If we sub Q equals V over T into equation 1, we get a new equation of P equals PQGH. This equation is just for simplicity. So if you want to retain the V over T in the first equation, you can always do so, as long as it is comfortable to you. Now let's take a look at wind power. The energy in the wind actually originates from the sun because the sun heats the air below it and allows it to rise due to its low density. As it rises, it leaves an area of low pressure close to the earth, and the surrounding air moves into this area. The air movement is called the wind, and interestingly, the rotation of the earth allows it to move in a circular pattern. And this is good because this circular pattern allows our wind turbines to generate electricity. Now let's look at my wind nodes. So the energy transformation that takes place in a turbine is wind kinetic energy to mechanical kinetic energy, and finally electrical energy. Now based on the image drawn, we consider the cylinder of air traveling towards the wind turbine has the same radius as the turbine. I'm going to use big V for volume and small v for velocity to avoid any confusion between them. So using the formula for the volume of cylinder, we can deduce that the volume of air is pi r square small v, where small v is the velocity of the wind. Why do we use velocity for the value of the distance instead of s? Distance v is actually calculated by assuming that the wind moves in 1 second. So using the equation small v equals to s over t, where t equals to 1 second, we find that s equals to small v, so the wind's velocity can be used as the distance in this case to calculate the volume of air travelling towards the wind turbine. Once again, we recall that density equals to mass over volume, so mass equals to density times volume. Therefore, if we sub big V equals to pi r square small v into m equals to p big V, we find that m equals to p small v pi r square. So we know that to find the kinetic energy of the air, we need to use the equation half mv squared. So if we sub m equals to p small v pi r square into the kinetic energy equation, we find that the kinetic energy equation for air is half p small v cubed pi r square. And if you want to make the equation simpler, we let the area of the circle be pi r square. So if we sub a into the equation, we get another equation for simplicity, which is half pa small v cubed. Again, subbing a into the equation is just for simplicity, so it's not necessary for you to do so if it's too complicated. Also, if all of this is confusing to you, please pause the video several times to understand the equations step by step. Now, we'll go into the advantages and disadvantages of generating hydropower and wind power. The advantages of both of these renewable resources are similar, where they are free, inexhaustible, does not pollute the environment, and they are both a clean source of energy. However, the main disadvantage of hydropower is that building a dam can affect the ecosystem in a particular area. The main disadvantage of wind power, on the other hand, is that wind power has a low power output due to external factors such as turbulence. So which of the two is a better choice? Well, it depends on what factors you are taking into account. Are you looking at the amount of power generated and power efficiency? If you are, then hydropower is suitable because it has a large power output. How about the amount of power needed, the location with the natural resources you need, and most importantly, the budget to build a dam or a wind farm? Those are things that should be considered according to the needs and purpose of a certain area. So to spice things up a little bit, I'm going to show you a short video on how these two renewable resources are generated in reality. I'm Rachel once again, and thank you so much for watching.
Okay, here's how it works. First, a wind turbine blade works sort of like an airplane wing. Blowing air passes around both sides of the blade. The shape of the blade causes the air pressure to be uneven, higher on one side of the blade and lower on the other. And that's what makes it spin. The uneven pressure causes the blades to spin around the center of the turbine. On the top, there's a weather vane that's connected to a computer to keep the turbine turned into the wind so it captures the most energy. Now the blades are attached to a shaft which only turns about 18 revolutions a minute, and that's not nearly fast enough to generate electricity by itself. So the rotor shaft spins a series of gears that increase the rotation up to about 1800 revolutions per minute. And at that speed, the generator can produce a lot of electricity. So why are wind turbines so tall? Well, the higher up you go, the windier it is. More wind naturally means more electricity. And in many cases, larger turbines can also capture wind energy more efficiently. The blades can sweep a circle in the sky as long as a football field. Now what's really cool is that even a small wind farm, like this one in Wyoming, can generate enough electricity to power more than 9,000 homes.
170,000 cubic meters of water flow past here every minute at almost 60 kilometers per hour. The electricity that powers the province. Most hydroelectric stations use either water diverted around the natural drop of a river, such as a waterfall or rapids, or a dam is built across a river to raise the water level and provide the drop needed to create a driving force. Water at the higher level is collected in the forebay. It flows through the plant intake into a pipe called a penstock, which carries it down to a turbine water wheel at the lower water level. The water pressure increases as it flows down the penstock. It is this pressure and flow that drives the turbine that is connected to the generator. Inside the generator is the rotor that is spun by the turbine. Large electromagnets are attached to the rotor located within coils of copper wire called a stator. As the generator rotor spins the magnets, a flow of electrons is created in the coils of the stator. This produces electricity that can be stepped up in voltage through the station transformers and sent across transmission lines. The falling water, having served its purpose, exits the generating station to the tail race, where it rejoins the main stream of the river to continue the cycle of creating clean, renewable energy for Ontario.